In the last video, we took a look at the idea of setting up memory in our operating system. In this video, we're going to be taking a look at how we can allocate memory for the kernel using Kmalloc. Kmalloc is a specific function that's typically used to allocate memory that is used by the kernel. It's kind of complementary to the malloc functions that you would typically see in C. Those ones allocate memory for user space. This one is more specific to the actual kernel itself. The way that this is going to work is we're going to initialize some space for the kernel to be able to use for memory purposes. And we're going to see how that general setup is going to work. This will help us get oriented with the idea of allocating memory. And we'll finish up the memory allocations that we need before we start to move on to some of the other ideas related to our operating system development. So to set this up, we are going to create a call in our main directly under our initialization of memory. Oops. And we're going to call that Kmalloc init. And what we do here is we provide the size of the memory that we want to declare. So 0x1000 would be just like a single block of memory in our current memory setup. So this would be the value that we are going to use. Now we're going to set all this up inside of a file named, we'll call it kmalloc.h. And we'll have a complementary, of course, kmalloc.c for this as well. So we'll do kmalloc.c. And we'll have our kmalloc.h. And inside of here, we're going to set up this init or kmalloc init function. So we have this function here. This right here is going to be a void function. So it's a void function that we have available here. We're going to just also declare this in our header before we forget to actually do that. And from here, we're going to set up the actual logic for our memory allocation. So the very first thing that we really need to do is we need to keep track of the memory that's being allocated and any information that's associated with this. And typically, we would do this by keeping track of the start of the memory and the size of the memory. Now, we're going to refer to this as heap memory, generally because when we use things like malloc, we're generally working with the actual heap memory, rather than working with something like, say, stack memory. Typically, we refer to this as the heap when we're working with malloc. So that's the terminology that I'll use as I'm going through this actual kmalloc setup here. So I have a start to the actual malloc. And then what I have is I have a heap size. So I have a size and a start, and that's generally how we're going to be able to set up the actual heap itself. We typically also keep track of another thing called a threshold. We won't worry about this too much because we don't really need it for our initial setup, but later on we will use this value, and we'll discuss that a bit more when we do. The final thing that I'm going to keep track of is just a boolean to tell me if we have actually initialized our kmalloc. It's going to start as false, and we'll set it to true once we finish inside of the allocation. The way that the allocation is going to work is, as we saw, we would have a specific value that we would put inside of here, be uint32t of initial heap size. And what we'll do is when we initialize this, we're going to set the heap start equal to a memory location. And that memory location is going to be just an area of memory that we can find that's going to be generally open and available for us to be able to use. I'm going to refer to it as kernel malloc. And I'm going to declare it inside of memory.h. The reason being is because we're going to use the value inside of memory.h, so I figure it's easiest to put it into that file and just reference it here. So we'll include our memory.h, and then over in memory.h, we'll define this. And generally the way that we would define this is, so our kernel start is at C0000000, and generally what I would suggest doing is to start the actual value for this, the kernel underscore malloc is what we called it, at 0xd000000, like this. And the main reasoning behind this is just because it's going to allow us to create some space between that kernel start and the actual memory associated with the kernel. So just before I leave here, I'll just make sure, it looks like I missed 10. Just want to make sure that I have all the zeros that I require inside of here. That way I get the proper memory location set there. That all looks good. So we'll come back over here. So this is the actual start of the allocation, right? So it starts at that location that we set. And then we're just going to initialize our heap size to be 0. I'm going to initialize my threshold to be 0 as well. And I'm going to set kmalloc initialized to be true to say that we have now initialized our kernel memory allocation. Now from here, what we want to do is we want to update the actual setup of the heap, and we can do that using a call to a function called changeHeapSize. We're going to give it the initial heap size as a value. Now what we'll do here is we'll set up this changeHeapSize function. It's just going to take in an int that is the new size. And just before I forget, I'll place this into the header as well so that we have that all set and good to go. And now what we want to do with this is we want to basically calculate the locations of the pages for this set of memory. So we could say that the old page top is going to be equal to the ceiling division of the heap size. I'm going to divide it by this value right here, which is our memory size generally. So this is going to give us the location of the old page top. And then similarly, the new page top is going to be at ceiling division of the new size with 0x1000. And if you're looking at this, you'll notice that when this first initializes, this value here will evaluate out to 0. This value here should evaluate out to 1 because the new size is starting at 0x1000, right? Now this ceiling divide function is something that we defined inside of our util. So we need to include this util.h in order to access that. So let's go ahead and include that up here. And that'll be good. So then from here, what we're going to do is we're going to calculate the difference between the page top and the old page top. So between the new and old. And then what I'll do is I'll say for each of the values from I equals 1 to the difference, we are going to set up the actual memory in physical memory. So what we're going to do is we're going to allocate a page frame. Then we're going to map that page frame into its respective page tables and page directories. So first things first, we're going to get the actual physical location memory where we're going to place this. We're going to do that inside of a function called Kmalloc page frame, which is not something we've declared yet, so we need to do that. I'm going to place this in memory because it's generally going to be usable for a few different purposes. So memory is a good place to place this. So we're going to say memory here, and then I'm going to go ahead and actually define this inside of memory.c. So let's come over to memory.c and take a look at this function here. So we want to do our alloc page frame, right? So it's going to return a uint32t, and it's called, again, alloc page frame. And what we're really going to do here is we're just going to set up the actual page frames inside of that physical memory location. So you'll remember that we have this like physical memory bitmap, and this is representing the actual, memory locations that we have. And we initialize this and we set it up with this init. And basically what we're going to do is we're going to populate this with the data that we are initializing from our kernel malloc, okay? So we're going to set up a uint32t start. So this would be the starting location. And we just have to do a little bit of a calculation to get this aligned properly. So we can take this page frame min, divide it by 8. And then we can add it to the page frame min, anded with 7. And we're basically going to check to see if this is equal to 0 or not. If it's not equal to 0, we're going to do this with a 1. Otherwise, we're going to do it with a 0. And just generally when you're taking a look at this, just kind of breaking down these sorts of statements to understand exactly what's going on here, right? So this page frame min, which generally was set to this value here, the division of the memory low by this 0x1000, right? We're dividing this up into 8. When you're thinking about this physical memory bitmap, remember that it's, of course, a bitmap, right? So when we're taking a look at this, we're looking at individual bits. When we're dividing things up, we're generally dividing up into bits here. And then this final piece here is really just taking a look at this being anded with 7. So we're really looking at, some of those final bits there to determine, exactly what the values are. And we're really doing this as like an alignment purpose. So we're just making sure that our pages are going to be set and aligned. And we do a very similar thing with the end as well. We just do it with the page frame max. The page frame max, of course, so like the min is the starting point, the max is going to be the end point, right? So we do this exact same process, just with the subtraction instead of an addition, right? So it's just slightly different, but same sort of idea, same sort of process. We're just making sure that everything is going to be properly aligned like this. And then you'll see here with this loop that it will help to clarify exactly what's happening with these calculations, right? So I'm going to set up some variable, I'll just call it b, and I'm going to set it equal to the start, and it's going to go into the end, and we'll increment it each time. And what I'm doing here is I'm grabbing a single variable called a byte, and I'm going to set that equal to the physical memory bitmap value at b. So this is going to be currently at the start of this value here, and we're going to get this value out of that physical memory bitmap, right? Now we're going to take a look at that byte, and basically what we're trying to determine is if this is actually in use or not. So if it's equal to 0xff, we're going to continue, so skip over that particular byte. However, on the other situation, if it's not currently set equal to 0xff, what we're going to do is we are going to set up, the memory allocation. So the I is going to equal to, it's going to start at 0, it's going to be less than 8. Remember, we're doing this as generally a bitmap, so we're going to be setting up these, 8 bits that are associated with this memory location. And what we're going to do is we're going to set our first thing, which is used. So used is going to be equal to that byte value that we retrieved. And we're going to take that and we're going to shift it by I ampersand 1. What this does is it retrieves the used value out of this value that we retrieved out of the physical memory bitmap. So when we're taking a look at those memory locations, remember that we have some different flags that are on there which are going to tell us information about this memory address. In order to determine if the value is used, what we're doing is we're shifting by I in order to see if the value is equal to 1. The reason for the shift is because we want to get it to be either a 1 or a 0. So we're shifting over by I in order to get it over to basically the first digit there so that it becomes either a 0 or a 1. That's the general idea of what we're doing here. What we're going to do is we're going to say, so if this is not used, then what we'll do is we'll say, okay, take that byte, and we're going to XOR it with -1 XORed with the byte. We're going to AND that with 1 shifted by I. And really this is basically just reversing this process here. We're basically setting this so that we're actually setting the byte to be used. And then what we do is we place it back in that physical memory bitmap. We place it at that location B is equal to byte. At this point, we increase our total alloc to say that we have now increased the number of memory allocations that we have done inside of our memory. Now from here, what we're going to do is we're going to get that physical memory address. The way that we do that is we take B, we multiply it by 8, we multiply it by I, right? And then we multiply this whole thing by 0x1000. So basically we're going to take that byte, right, that value B that we have, we multiply it by 8. Again, remember that we're working in these sections of, this bitmap. And then we're going to multiply it by I, taking us out to our current location. We multiply that by 0x1000, which is the size of the actual allocations of memory, and that will give us the address as a result. Finally, we will return that address back to the user to be able to give them that physical address. Now, in addition to this, in some cases this may fail. For now, what we're going to say is that we'll just return 0 as a result if things happen to not work out. This will just be the default return. And at some point later on, we should come back to this probably and do something a little bit more interesting with this, throw some sort of error or do something in particular with this sort of case. But for now, returning 0 is going to be totally fine. So that gives us our really basic setup of our PMM alloc frame, right? So that's the main idea of what we're really doing here. Now, what we want to do after we've got that physical address is we want to actually map that address properly, right? And I'm going to do this using another function, which I'm going to call the memmapPage. The memmapPage function is going to take in basically 3 different arguments. It's going to take in a virtual address, a physical address, and a set of flags, and it's going to map using those different values. So the way that we're getting these different things is, so the first was our physical address, so it's the Kmalloc plus the old page top times 0x1000 plus I times 0x1000. That'd be the location of that virtual address, right? And then we have the physical address, which we retrieved from this PMM alloc frame, right? And then I'm just going to wrap the text here so you can see it a little bit better, right? And then the final thing here is what flags we want to set on this. Now we want this memory generally to be writable. So the main flag that I'm going to set here is page flag write. And those are the main details that we need for this mapping of the page. So let's go ahead and implement this as well. We're going to implement this inside of memory.c. This function is a fair bit more complicated than the previous one, right? There's a bit more work that's going to be required for us to be able to get this one up and running. So like I said, generally the main structures, we have a virtual address, we have a physical address, and we have a set of flags. And in this general setup here, what I'm going to do is I'm going to start by creating a pointer to the previous page directory. We're going to set it equal to 0 to start. Now what we want to do is we want to take a look at a few different situations here. So if the virtual address that we have is greater than or equal to the kernel start, then what we're going to do is we're going to say, well, the previous page directory is going to be equal to the get current page directory. We haven't defined this yet, so just going to define this now. This function here is generally going to allow us to get the current page directory that we are currently using, right? So what this will return is it will return back a uint32t pointer. And that pointer is going to be retrieved just using an ASM call. So we can do an ASM volatile, and all we're really going to do is we're just going to move the contents of CR3 into the PD value that we've defined, right? So that's all we're going to do here. And then we're just going to take this and we're going to add it to the kernel start. And then what we'll do is we'll just return this uint32_t of the PD. The reason why we add on the kernel start is because, remember, because we're using upper half kernel, the kernel is starting at that C000 location. So when we get this back, we have to add this on in order to get us to the actual location of the memory address, right? So that's how we get the previous memory directory. So with this previous memory directory, what we're going to say is if the previous page directory does not equal the initial page directory, so if we're no longer on the initial directory, then we're going to actually change the page directory. And we're going to change it to the initial page directory. To change the page directory, we're going to use a similar sort of process as getting the page directory. We're just going to do a mem change pagedir, uint32_t star PD. We're going to go ahead and calculate out the location of the page directory. We do this by doing the following. So we do a uint32_t of PD, and then we just subtract it from the kernel start. You'll notice that we're basically just doing the opposite sort of process of what we did here, right? This one was adding on the kernel start. Here we're basically just dereferencing the pointer and then subtracting the actual kernel start, right? So that's generally what's happening here. Realize that I should do PD equals. And then again, we do an ASM volatile, but this time we're going to move the value that we computed. We're going to move it into EAX. And then we're going to move EAX into CR3. Again, the main reasoning for doing the two moves is that we can't move directly into CR3. We have to move from a register to CR3. So we write to the register first, and then we place that result into CR3, and we are good to go. So that's generally how we're going to set this up. Now, once we've got this all sorted, if it needs to be, we're going to go ahead and calculate the page indexes associated with the virtual address. So we want to get the PD, the page directory index, as well as the PT, the page table index. These locations are going to be at the virtual address shifted by 22, and the PT index is going to be at the virtual address shifted by 12, and we would AND this with 0x3ff. So those are the locations of those two values. Now, once we have the locations of those two values, what we're going to do is set up a pointer to our page directory. I'm going to call this rec pagedir. We actually have to define this still. So this is going to be inside of memory.h. And what this looks like is I define it as rec underscore pagedir. It's a uint32t pointer to a particular address that we use for these pagedirs. That particular address is 0xFFFFF000. That's the location of that. Now, the other thing I'm going to define here while I'm here is going to be the rec page table. This one allows us to index at a value I. The location of this is the uint32 pointer of the following calculation. It's 0xFFC, FFC 0, and then 0000. Just want to make sure that I align that properly. And we're going to take that and we're going to add it to the index I that we have. And we are going to shift that by 12, like this. So that's generally what that calculation is going to look like. So this gives us these two values. Now, there are a few other things that we may need to define inside of here. We have the page right present and the page flag right. There's one other page flag that we actually need as well, just while we're here. It's the page flag owner. And this one is 0 shifted by 9, or sorry, 1 shifted by 9 rather. So this is the other value that we need to find inside of here. So that should get us all set to finish up our definitions here. So where we got here was we were able to get the PD index and the PT index. So we get the page there, right? And then what we do is we determine the specific page there associated with this, or the specific page table rather, using rec underscore page table at PD index. So we're just taking this index and we're using it to reference this table here, right? And now we just need to take a look at this data in order to determine where we need to map this appropriately. So here what we're going to say is, we'll say if not pagedir at PD index and page flag present, then what we're going to say is we're going to say the uint32t of ptpaddr is equal to pmm alloc page frame. So we're going to alloc a page frame. So this is going to give us back that physical address like we were doing previously. And then what we do is we take the page there at the PD index, and we set it equal to that ptpaddr that we just found, and we just OR it with all the flags that we want. So the flag present, we want it to have the flag right, we want it to have the flag owner, and we'll OR it with whatever other flags were provided. So this is essentially just initializing this page directory with the address as well as any of the flags that we wanted to set on that. And then finally, like we did in the previous few videos, we invalidate the virtual address once we're done with that, right? So we just invalidate that value. And then what we're going to do is we're just going to initialize out the page table to be all zeros. So just below this, we say for uint32 underscore t I equals 0, I is less than 1024, I plus plus, and we're just going to take pt at I equal to 0, right? So we're just initializing out those values to be 0. Now, outside of this if statement here, we're going to take the pt at the pt index, and we're going to set it equal to the physical address, and we're going to OR it with the page flag present. We're going to OR that with flags as well. So do you see how we've really created this mapping? So the page directory has this physical address that we're setting here, right? And then we have the page table, which is also setting that physical address with the flag specified. So you could see how we're building up the actual structure of our tables here. Now what we're going to do is we're going to increment a value here, which is just tracking the number of V pages that we have, number of virtual pages that we've declared. And I don't think that we've declared this yet so far. I'm going to declare this just down here. And we're going to set it equal to 0 to start. And what we'll do is we'll just declare the actual variable up at the top here. It'll just be an integer value. just like that. Okay, so that gives us a pretty good structure. There's a little bit more that we need to do to wrap this up. So we have this sort of structure here. We have incremented the V pages, right? And then once this is done, again, we invalidate our virtual address. And then the final piece here that's required is we need to take a look at the previous page dir. If it's not equal to 0, we need to sync up the page dirs. So we need to actually synchronize up our page directories. And additionally, if the previous page dir does not equal the initial page dir, then we actually want to change our page directory to be the previous page directory. So we want to switch back over to that page directory. So this we've already defined, we've already set up, so that's all good. It's just this sync page directories. It's the last piece that we need here. So let's go ahead and set this up. So general processing for this is going to be the pretty standard way that we would do our mapping here. So what we do is we say for int I equals 0, I is less than the number of page directories, I++. If the page directory is used at that particular index, then what we do is we go ahead and get that page dir. And then what we do is just we run through from I equals 768 up to 1023, so those upper bits of the entry. And we set the page dir at I equal to the initial page dir at I, ANDed with the negation of the page flag owner. So here we're just updating the page dir entries, and we're setting it so that it's going to be, using that initial page dir and just negating the page flag owner so that it's being set properly on each of those bits. And that's the main things that we really need for this actual mapping. So this is the main way that we're mapping through that data. Now we want to make sure that we have all these declarations inside of our headers. So that's just the next thing that I'll do here. So I see I have my PMM alloc page frame, right? The other thing that I need here is I need my mem get current page dir. I need the void of mem change page dir. That one takes in a uint32t pointer. We need sync page dirs was the other function that we had, and then we had mem map page, which took in a uint32t of virtual address, a uint32 underscore t of physical address, and a uint32 underscore t of flags. And I think that those are the main things that we needed to define here. I think everything else is defined fine in this area here. I think Kmalloc is all set and ready to go as well. So at this point, we can give this a try and see if we've got everything up and running successfully. The final thing I'll just check here is just my includes, because I've probably forgotten some. It looks like I have. For this, I do need to also include my standard int.h. I also need to include, I have util.h, I have memory.h, and I need to include the value for Kmalloc.h. There we go. So that should get us all set. What we'll do here is we'll set up the makefile, and we'll take a look and see where that takes us. So let me come over here into my makefile. And really all we need to do here is we just need to compile through our entries for Kmalloc. And let me just close this off here. Then we just want to link in that Kmalloc. Like this. Now there's one other thing that I haven't done here that I should, and that's that when I'm taking a look at my GCC, I realize, well, I've just recently reinstalled this, so this is actually in a slightly different directory. That's okay. I'll just update this for my computer here. You probably won't need to do this. That's all right. But one thing you may need to do, I've seen some people discussing this, is the loader you can actually also use the cross compiler on. In some cases, you may actually run into some problems with the cross compiler loader. So what I found was that when I wasn't using the cross compiled loader, what was happening was it was actually giving me errors because I think that something has happened where it's deprecated out this 32-bit linker loader file, so we can actually use our cross compiler instead. So we could just do LD here and then just replace this with $LD, and that's going to fix a lot of problems if you encounter that sort of issue. Okay, cool. So let's try making this and see if it works or if it breaks. And it does break, so we were kind of expecting that. That's okay. It looks like init memory is implicitly defined, which is kind of interesting because I think that it should be inside of here unless memory isn't here. Oh, it looks like I don't have memory here. That'll of course cause some problems, so let's go ahead and fix that. There we go. And I do have one other error inside of here. Actually, this is an older error. I think it came from a previous video. It's just, I fixed this one as well. It's in keyboard.c, just based on the ordering of things in the actual imports here, it actually causes an error in compiling because it doesn't recognize the function properly. It's always a little bit of a pain that we have to make sure that our includes are in the right ordering, but that's okay. Basically, interrupts has to come after the util.h, like this. And that should generally help us. There we go. Now, a few other things here. It looks like, we have some conflicting types between PM alloc page frame. So let's just take a look at that here. I probably just typed things in wrong. So we were taking a look at PM alloc page frame. Let's take a look and see here. PM alloc page frame I have as a uint32, and over here I have it as a void. So it should be uint32_t. And just to make sure, yeah, it's not a pointer. Okay, cool. Let's try that again. Okay, so far so good. We just have one other error, junk CR3 after register. So I've made a mistake in my memory.c where I'm allocating out the actual assembly code here. Let's see here. So I moved CR3. I think this one is okay. There's probably one other one where I have a problem. This one right here looks mostly okay. Because I move %0, EAX, and then I move EAX. Oh, I missed a comma. That's our problem. Make one more time. Looks like we are good. QEMU system i386 kernel.iso. Give that a try. And it looks like we're okay. Nothing's crashed. Our keyboard is working. So I think everything is good to go. So this gives you an idea of how you can implement a Kmalloc actual implementation in your operating system. Our implementation may not have been the best, but it is one that will serve us well for the time being as we continue to develop on these aspects of our operating system. We'll probably come back and improve these types of functions as we continue on, but for now, this is going to be good enough for us. So thanks so much for watching this video. I'll see you in the next one.